Hello everyone and welcome to this session on basic peripherals and their interfacing with 8086 microprocessor. This session is a part of the Module 3 of the course CS305 Microprocessors and Microcontrollers for the 5th semester BTech Computer Science and Information Technology students under the APJ Abdul Kalam Kerala Technological University. Myself Anu Maria Joykutti, Assistant Professor, Department of Computer Science and Engineering, Rajagiri School of Engineering and Technology. First, let's see in brief about the peripheral devices. In the minimal working system configuration of a general microprocessor, a keyboard, a display system, a memory system, and the I/O ports are considered along with the CPU. In general, all these devices are known as the peripheral devices. Along with these devices, there are certain dedicated peripheral devices like the PIC or the Programmable Interrupt Controller, the DMA controller or the Direct Memory Access Controller, the CRT controller, etc. The microprocessor is seen as the heart of the system, while all the peripheral devices including memory are built around the microprocessor. Since a processor without memory is not much meaningful, the primary memory is also considered as an integral part of a microprocessor system. Most of the peripheral devices are designed and interfaced with a CPU either to enable it to communicate with the user or an external process and to ease the circuit operations so that the microprocessor works more efficiently and effectively. The use of a special purpose peripheral integrated device simplifies both the hardware circuits and the software considerably. The memory acts as a media for communication between a peripheral with the CPU. While the memory is often treated as a peripheral, the peripheral devices are often treated as memory locations. Thus, as far as the CPU is considered, there is no special difference in the method of handling memory or peripherals except for the use of the respective control signals. In the coming slides, we'll be seeing in detail about the method of interfacing memory as well as the I/O ports. First, let's see how memory is interfaced with the 8086 microprocessor. The memory is used for storing program as well as the data. Now, the memory can be broadly classified into three types, which is the processor memory, the primary or the main memory, and the secondary memory. The processor memory are nothing but the registers that are inside the processor. They store data and results temporarily. There should not be any speed disparity between the processor memory and the microprocessor. And the processor memory or the register memory are having usually high cost. The second category is the primary or the main memory. This is the storage area that is directly accessed by the microprocessor, which is outside of the microprocessor, but it can be directly accessed by the microprocessor. The primary memory is used to store programs and data prior to the execution. So in order for a program to execute, it should be present in the main memory. The primary memory also should not have any kind of speed disparity with the processor. The semiconductor memories using CMOS technology are used for building the primary or main memory. Examples of primary memory are ROM, EPROM, static RAM, DRAM, etc. The last category is the secondary memory. The secondary memory is the storage media which consists of slow devices such as magnetic tapes and disks. This is used for storing large data files and programs such as the operating system, the compilers, the databases, the permanent programs, etc. Let's have a quick recap of the memory organization of 8086. The memory of 8086 is byte oriented. That means each of the memory location can store up to 1 byte or 8 bit of information. As we all know, the 8086 is a 16-bit processor. That means at a time the 8086 can act on 16 bit of data or 1 word of data. This 1 word or 16-bit of data is stored by two consecutive memory locations. One for the LSB or the least significant 8 bits and the other for the MSB or the most significant 8 bits. Now the address of the word is equal to the address of the LSB. The memory of 8086 is divided into two banks which are known as the even bank and the odd bank, also known as bank 0 and bank 1. Now the even bank is addressed in the case if A0 or the least significant bit of the address bus is equal to 0. And the odd memory bank is addressed when the BHE or the bus high enable signal is having a value of 0. This picture is a diagrammatic representation of the memory organization of 8086. As we told before, the memory of 8086 is divided into two parts, the even memory bank and the odd memory bank. The even address memory bank will have the data bits from D0 to D7, that is the lower order data bits D0 to D7 will be used for data transfer from the even address memory bank, whereas the higher order data bits DA to D15 will be used for data transfer from the odd address memory bank. Now, each of these memory banks are selected based on the chip select logic. So, the chip select of the even address memory bank is connected to the A node, that is the least significant bit of the address bus. When A node is having a logic 0 value, this even address memory bank will be selected. When the bus high enable signal BHE bar signal is having a low value, then the odd address memory bank will be selected. Next, let's discuss in detail about the various memory operations one by one and the corresponding values of the BHE bar signal, the A0 signal and the data lines that are used for these operations. The first operation is to read or write a byte at an even address. So here we need to write at even address, that means the even address memory bank has to be selected. In order to select the even address memory bank, the A0 signal should be 0 and the BHE bar signal should be 1. The data lines that are used are D7 to D0. The next operation is to read or write a byte at an odd address. So here the odd address memory bank has to be selected. For that purpose, the BHE bar signal should be 0 and the A0 should be 1 so that the even address memory bank is not selected. The data lines that are used for this purpose is D15 to D8. Next operation is to read and write a word. That means 2 bytes has to be written at an even address. So here we need to write both at the even address memory bank and as well as the odd address memory bank. So for this purpose, both the BHE bar signal as well as the A node signal should be at a value of a logic low value, that is 0 value. And the data lines that are used as D15 to D0. Here 16 bits or one word has to be written, so all the bits in the data lines are used. Next operation is to read and write a word at an odd address. So here a word needs to be written at an odd address. That means the LSB should be written at the odd address memory bank and the MSB has to be written in the even address memory bank. For this purpose, we require two bus cycles. In the first bus cycle, the odd address memory bank has to be selected. So for this purpose, the BHE not signal should be 0 and the A naught signal should be 1. The data lines that are used are D15 to D0. So here the first byte is transferred to the odd bank or transferred from the odd bank depending on whether it is a read or a write operation. Now in the second bus cycle, the even address memory bank has to be selected. So for this purpose, it has to have the BHE bar signal should be 1 and the A naught should be 0. So, and the data lines that are used are from D7 to D0. The semiconductor memory can be broadly classified into two types, the RAM or the random access memory and the ROM or the read-only memory. Now, just like the name suggests, the read-only memory can only be used for reading. That means there are no write operations that can be performed on the ROM. The random access memory can be used for both read and write operations. The random access memory is further divided into two categories known as the static RAM and the dynamic RAM. The semiconductor memories are organized as two-dimensional arrays of memory locations. For example, a 4K into 8 or 4 kilobyte memory contains 4096 locations, where each of this location contains 8-bit data, and only one of the 4096 locations can be selected at a time. Once a location is selected, all the bits in it are accessible using a group of conductors called the data bus. So obviously for addressing 4K bytes of memory, 12 address lines are required. In general, to address a memory location out of n memory locations, we will require at least small n bits of address. That is, small n address lines where small n is equal to log to the base 2 of n. Thus, if the microprocessor has n address lines, then it can address n locations where 2 to the power of small n is equal to n. If only p out of n locations are to be interfaced, then the least significant p address lines out of the available n lines can be directly connected from the microprocessor to the memory chip, while the remaining n minus p higher order address lines may be used for address decoding. Address decoding as an input to the chip selection logic. The memory address depends upon the hardware circuit that is used for decoding the chip select. The output of the decoding circuit is connected with the chip select of the memory chip. Now let's see the general procedure that is used for static memory interfacing with 8086. The first step is to arrange the available memory chips so as we will be obtaining 16-bit of data bus width. The upper 8-bit bank is known as the odd address memory bank and the lower 8-bit bank is known as the even address memory bank. The second step is to connect the available memory address lines of the memory chips with those of the microprocessor. Also, we need to connect the memory read and the write inputs to the corresponding processor control signals. The 16-bit data bus of the memory bank is connected with that of the 8086 microprocessor. The third step is to use the remaining address lines of the microprocessor, the BHE signal and the A0 signal for decoding the required chip select signals for the odd and the even memory banks. The chip select of the memory is derived from the output of the decoding circuit. The procedure that was explained in the previous slide will become more clear when we solve problems on memory interfacing with 8086. As a good and efficient practice, the address map of the system should be continuous as far as possible. That is, there should be no windows in the map and no fallback space should be allowed. A memory location should have a single address corresponding to it. That is, absolute decoding should be preferred and minimum hardware should be used for decoding. In a number of cases, linear decoding may be used to minimize the required hardware. Now let's consider a few examples on memory interfacing with 8086. In the first problem, we are interfacing two 4K into 8 EPROMs and two 4K into 8 RAM chips with 8086. We need to select the suitable memory maps. Here, as the solution, we know that after resetting, the IP and the CS are initialized to form the address FF0H. Hence, this address must lie in the EPROM. The address of the RAM may be selected anywhere in the 1 MB address space of 8086. But in order to make the memory map continuous, we'll select the RAM address such that the address map of the system is continuous as shown in this memory map figure. So here there is total 8K bytes of EPROM needed. Two 4K into 8 EPROMs, that means there are total 8K bytes of EPROM. This total 8K bytes of EPROM need 13 address lines. So we'll be using the lower 13 address lines for this, that is from A0 to A12. Since 2 raised to 13 is equal to 8K. So that is how we get the number 13. The remaining higher order address lines, that is from A13 to A19, are used for decoding to generate the chip select. The BHE bar signal goes low when a transfer is at odd address or higher byte of data is to be accessed. Let us assume that the latched address, BHE bar and demultiplex data lines are readily available for interfacing. So, as it is clear from the figure, that is the memory map, we see that starting from the address FFFFH, 8K locations till FE000H is allocated for the EPROM. The remaining, the next 8K, the next set of 8K locations starting from FDFFFH till FC000H is allocated for the RAM. So only we require A0 to A12 address lines for selecting the EPROM addresses as well as the RAM addresses. The remaining address lines, that is A13 to A19, are used for the decoding logic. From the memory map, we can also see that the value of A13 is always 1 for EPROM and the value of A13 is 0 for RAM. That means the A13 bit is used for distinguishing whether we need to address the EPROM or the RAM. Next, we'll see how the memory chip selection is done for this particular problem. So for the decoder circuit, which does the chip selection, we need three inputs. The first input is the A13 input, which is 0 if it is the RAM that has to be selected, and it is 1 if it is the ROM that has to be selected. The other two inputs for the decoder is the A0 and BHE bar. The A0 will be 0 if it is the even address that has to be selected, and the BHE bar will be 0 if it is the odd address that has to be selected. So all these three inputs are the input that needs to be given to the decoding circuit. Now let's see in detail about each of the different operations. So if the operation that has to be done is a word transfer on the RAM, that is the bits D0 to D15, all the 16 bits of the data bus are required. So in that case, here it is the RAM that has to be selected. So for that, the A13 bit should be 0. And it is a word transfer, so that means both the even address bank as well as the odd address bank has to be selected. So for that, both A0 as well as BHE bar should be 0. Next operation is to do a byte transfer, that is on the lower order data bus bits, that is from D7 to D0. So in that case, again it is the RAM that has to be selected. So for that, A13 is 0. Since it is the lower order data bus that needs to be that will have the data, that means it will be put in the even address memory bank. So for that, the A0 should be 0 and BHE bar should be 1. Next, we need to do a byte transfer on the higher order using the higher order data bus. So that will be put into the odd address memory bank of the RAM. So here again the A13 should be 0 to select the RAM, and because it's the odd address memory bank, the A0 should be having a value of 1 and BHE bar should be having a value of 0. Next, if the operation is to do a word transfer of the ROM, then we need to select the ROM. So for that, the A13 should be having a value of 1. Because it is a word transfer, both the even address memory bank as well as the odd address memory bank has to be selected. So for that, both A0 as well as BHE bar should be having a value of 0. Next, if we need to do a byte transfer on D0 to D7 for the RAM, for the ROM, then the A13 bit should be again 1, and since it is the even address memory bank that has to be selected, the A0 bit should be having a value of 0 and the BHE bar should be at 1. Next, if we need to do a byte transfer on D8 to D15, that is, it will be moved on to the odd address memory bank of the ROM. Again, because ROM has to be selected, the A13 bit is 1. Because it is the odd address memory bank that has to be selected, the A0 bit is 1 and the BHE bar should be at 0. This figure is the interfacing diagram of the memory system. As we discussed in the previous table, the decoder circuit has got three inputs, which are the BHE bar signal, the A0 signal and the A13 signal. Now, the decoder circuit will get these three inputs and decodes it into 8 outputs. These 8 outputs are used as the chip select logic. Now, as we said in the previous slide, when the value of A13 is 0 and A0 is 0 and BHE bar is 0, that means the RAM has to be selected and both the even addressed memory bank and the odd address memory bank of the RAM has to be selected, because there has to be a word transfer on the data bus D15 to D0. So as we see, the decoder will then select the output 0. This output 0 is given to both this AND gates, which will produce the output CS4 bar and CS3 bar. So the chip select 3 and the chip select 4 are generated. That will select the odd address memory bank of the RAM and the even address memory bank of the RAM. Similarly, when the A13 is 0 and A0 is having a value of 0 and BHE bar is having a value of 1, that means the even address memory bank alone of the RAM has to be selected. So in that case, when A13 is 0, A0 is having 0 and BHE bar is 1, the output of the decoder is 1. That means the chip select 4 is enabled. The chip select 4, as we can see, is for the even address memory bank of the RAM. Similarly, when A13 is having a value of 0, A0 is having a value of 1 and BHE bar is having a value of 0. In that case, the output of the decoder is the output 2. So we can see from the figure that the output 2 will enable the chip select 3. So chip select 3 is for the odd address memory bank of the RAM. Similarly, when the A13 value is 1, A0 and BHE bar are having values of 0. In that case, the output of the decoder is the 4. Is 4. So we can see that 4, when the output of the decoder is 4, it will enable both CS1 and CS2. That means both the odd address memory bank as well as the even address memory bank of the ROM will be selected. Next case is when A13 is having a value of 1, A0 is having a value of 0 and BHE bar is having a value of 1. In that case, the output of the decoder is 5. So we can see from the figure that when the output of the decoder is 5, that means the chip select 2 is enabled. That means the even address memory bank of the ROM is getting selected. The last case is when the A13 is having a value of 1, A0 is having a value of 1 and BHE bar is having a value of 0. In that case, the output of the decoder is 6. So as we can see from the figure, when the output 6 is given, the chip select 1 is enabled. That means the odd address memory bank of the ROM is getting enabled. Now let's see another problem, which is to design an interface between the 8086 CPU and two chips of 16K into 8 EPROM and two chips of 32K into 8 RAM. We need to select the starting address of the EPROM suitably, and the RAM address must start from 00000H. Now, we know that after reset, the process starts from FFFF0H, and this address must lie in the EPROM. So for that, we will select the EPROM address from FFFFH. The starting address of the EPROM is from FFFFH. From there, 32 KB address space is reserved for the EPROM. So it will end at F8000H. Next, the RAM address must start from 00000H. From there, 64 KB address space is reserved for the RAM. So the RAM address space ends at 0FFFFH. So here, as we can see that the memory map is not continuous. Now, for the EPROM memory mapping, we require A0 to A13 address lines because 32 KB address has to be 32 KB memory has to be addressed. So 32 KB means 2 raised to 4, 2 raised to 15 address has to be 2 raised to 15 address lines are required. So for that we will be using the A0 to A14 address lines. The remaining A15 to A19 address lines will be used for the chip select logic. In the case of the RAM, we require 64 KB address space to be mapped. So we require for 64 KB address locations, we require 64 KB is equivalent to 2 raised to 16. So that means we require 16 address lines from A0 to A15. The remaining address lines A16 to A19 will be used for the chip select logic. This figure shows the interfacing diagram of the above memory system. It is not advantageous to use a decoder to implement the above memory map because it is not continuous. That is, there is some unused address space between the last RAM address, which is 0FFFH, and the first EPROM address, that is F8000H. Hence, the logic for the decoding circuit is implemented using logic gates as it is shown in the figure. Now, we said that the address lines A0 to A14 is used in the case of the row. So the remaining address lines A15 to A19 is used for the decoding logic. Similarly, in the case of the RAM, the address lines A0 to A15 are used, and the remaining address lines A16 to A19 is used in the decoding logic. So A15 to A19 is given to a 5-input NAND gate which produces the output C, and A16 to A19 is given to a NAND gate which will produce the output C dash. So when C is selected, that means it is the row that has to be enabled, and if it is C bar, then that means it is the RAM that has to be enabled. It is clear from the memory map that A15 to A19 lines of the address will be having a value of 1 if it is the ROM, and A16 to A19 will be having a value of 0 if it is the RAM. So based on that, we have designed the decoding logic. So when A15 to A19 is having a value of 1, C is equal to C is the value of the output of that particular NAND gate is having a value of 0. So when C and DHE bar are given to the logic gate, it will enable the output CS1. That means CS1 is for the odd address of the RAM of the ROM. Similarly, when C and A0 are having a value of 0, then the CS2 or the chip select 2 is selected. The chip select 2 is for the even address bank of the row. Now, when BHE bar and A0 are both zeros, then the chip select 1 and the chip select 2 both will be selected of the row. So that means the even address bank as well as the odd address bank of the ROM will be selected. Similarly, in the case of the RAM, when C bar is having a value of 0 and A0 is having a value of 0, then the chip select 4 is enabled. Similarly, when C bar is 0 and BHE bar is having a value of 0, then the chip select 3 is enabled. So that means the corresponding even and odd address banks of the RAM is getting selected. When both A0 and BHE bar are 0, then both CS4 and CS3 will be enabled. That is, both the even address bank and the odd address bank of the RAM will be getting selected. So that was about how the memory is interfaced with 8086. Next, let's see how I/O devices are interfaced with 8086. There are two methods of interfacing I/O devices. The first method is known as the I/O map method, and second method is known as the memory map method. In the I/O map method, the devices are viewed as distinct I/O devices and they are addressed accordingly. Whereas in the memory map method, the devices are viewed as memory locations and they are addressed like we address a normal memory location. In the case of I/O map, all the available microprocessor address lines may not be used for interfacing. Whereas in the case of memory map, all the available address lines, that is all the available 20-bit address lines, are used for address decoding. In the case of I/O map scheme in 8086, at most 16 address lines, that is from A0 to A15 is used. Whereas in the case of memory map, like we said earlier, all the 20-bit address lines are used. The unused address lines in the case of I/O map will be always at a logic 0 level. Because all the 20-bit address are used in the case of memory mapped I/O, there can be as many as 1M I/O devices in the case of memory mapped I/O. The in and the out instructions are used for data transfer between I/O devices and processors in the case of the I/O mapped. In the case of memory map, since the I/O devices are treated as memory locations, all the memory related instructions that are used for communicating with memory can be used for data transfer. The IO map category requires less hardware for decoding as it uses less address lines, whereas in the case of memory mapped IO, it requires complex hardware for decoding as all the address lines are used. The IO map category, in the IO map category, the devices are addressed as IO devices itself. Hence, it requires the IORD and the IO write signals, that is the IORD and the IOWR signals are used for addressing these input and output devices. In the case of memory mapped IO, the devices are seen as memory locations. So the signals that are used are the memory read and the memory write signals, which are the MRDC and the MRTC signals. In the case of 8086, for IO mapped, a maximum of 16-bit address lines are used. That means it can address up to 64 kilobyte of input and output devices, or it can address up to 32 kiloword of input and output devices. In the case of memory mapped IO, all the 20-bit address lines are used for the IO devices. So in that case, there can be up to 1M devices. These 1M devices will be using all the 1 megabyte of memory map that is available, and hence nothing will be left as the program memory. Because of this reason, the memory mapped IO is seldom used in the case of 8086. The IO map is suitable for systems which require large memory capacity, and the memory map is suitable for small systems which require only very less memory. Now, in the IO mapped, as we said, because the devices are treated as IO devices itself, the M/IO bar pin is always a logical low. And in the case of memory mapped IO, the devices are treated as memory locations, and because of this reasons, the M/IO bar pin should be at a logical high. The actual method of interfacing IO devices with 8086 can be better explained with the help of a problem. The interfacing hardware always needs supporting application programs to carry out the desired operations. Hence, this interfacing example is accompanied with a supporting 8086 assembly language program. The problem is to interface an input port 74LS245 to read the status of the switches SW1 to SW8. The switches, when shorted, will input a 1, else the switches will input a 0 to the microprocessor system. We need to store the status in the register BL. The address of the port is 0740H. Now, the hardware interface circuit diagram is as shown in the figure. The address, the control, and the data lines are assumed to be readily available at the microprocessor system. Now, as we can see from the figure, in order to address this particular port, we require 16 address lines which are from A0 to A15. These address lines along with the control signal, that is IORD signal, forms the control logic or the decoding circuit of this particular interfacing system. So when the particular address and the IORD signals are available, the chip select of the 74LS245 port is enabled. So that means the 74LS245 port is selected. Now the switches are connected to the bits O0 to O7. So depending on which of the switches are shorted, the corresponding bit from O0 to O7 will get reset or set. And this data is passed to the microprocessor using the D0 to D7 data bus. Let's see the assembly language program that is required for the above problem. The first instruction is to clear the BL. For that, we will be moving a value of 00 to BL. Next instruction moves the 16-bit port address into the DX register. After that, using the IN instruction, the data from the port address that is given in DX is moved into AL register. And this is finally moved into BL register, and that is the end of the program. So after executing the program, the LSB bit of BL will correspond to the status of SWN switch, and likewise the MSB of BL will correspond to the status of SW8. The 1 indicates on or shorted switch and the 0 indicates an off or open switch. So that is all about interfacing peripheral devices with 8086 microprocessor. Thank you.